O, 2, 3, 4, 5. Okay, so why is that first oxygen a reasonable nucleophile?
That oxygen has a positive charge. You mean, oh, the nucleophile, sorry. It has a lone pair.
That makes it reasonable. Good.
Yeah.
Why is carbon 2 a reasonable electrophile?
It has attached to it a positive oxygen.
Good, because it's attached to an atom with a positive charge. Good. So
Yeah.
it's not the atom with the positive charge that's the electrophile, it's the attached atom. Okay.
Yeah.
All right, and you did a good, careful job of drawing the product from that. The previous time in the previous set, there were a bunch of problems where there was a neutral atom at the beginning of the string of arrows, but we were forgetting to change its charge to positive. But this one we got right. We changed that oxygen to positive. All right, so I'll take a look at the next. Why is carbon 3 a reasonable electrophile?
That carbon has a positive charge.
Good.
Carbocation.
That's right. Carbons with positive charges are electrophiles. And why is the chlorine a reasonable nucleophile?
It has a negative charge.
That makes things nucleophiles. Good. Okay, that's fine. Let's continue. Okay. Okay, check your work on this problem. Check, in particular, check the product that you drew.
Okay.
So the arrows are correct. The arrows are correct, but check the product that you drew.
Oh yeah, sorry. I added a positive charge. It should just be neutral since it started with a negative charge.
Yes. Okay, that's right. Okay, all right, so that was a mistake. So remember, so I think that we've made some good progress on learning those rules, but we are still making some careless mistakes. Remember, our goal is close to 100% accuracy for those types of pictures, because that's only going to be one part of harder problems, right? There's not many problems that are just going to be about drawing the product, but if we can't get that part right flawlessly, we're not going to be able to do the rest of the problem. So our goal is to get to the point where it's easy for us to draw those flawlessly. So how do you know that the new charge should be neutral rather than positive?
It is donating electrons, so it should be one step less negative.
How do you know that doesn't make it positive?
Well, it has a negative charge because of its ionic bond with sodium.
As you already drew. So the key thing is, remember that there's two questions you need to ask to draw the new charge. And in this one, you kind of focus too much on only one of them. One thing you need to know is whether the atom is gaining or losing electrons. But the other thing that is just as important is what charge did it start with? And that's what we didn't take into account enough here. You have to ask first, what charge did it start with? And then make it one step less negative. Okay.
Okay.
So that just takes practice. Maybe I shouldn't emphasize this too much, but I don't know, we can mention one other thing. Go back and put that positive charge back in, that mistake, for a moment. Now, look at the starting materials. What was the total net charge of all the starting materials? And you can ignore the spectator ion.
Just a positive one. Or a negative one, I mean.
On the hydroxide, yes.
Yeah.
So now look at the product that you've drawn. Now, with the product that you've drawn, and we'll continue to ignore the spectator ion, what's the total net charge of the product that you've drawn?
With that positive charge, there would be a net charge of 0.
Does that match the starting materials?
Not at all.
Right. So I'm just saying that's another way to catch that type of mistake, because the charges have to balance. The charges have to balance. If you started with a net charge of negative on the left, there has to be a net charge of negative on the right as well. I thought I would mention that. Maybe we don't need to make too big a deal about it, though, because we don't, in a way, we don't really need a backup way of checking our work. The rules are so straightforward that we should be able to use those to get the problem right anyway. But
Sure.
I did want to mention that is another danger sign that you can kind of glance your eye over. The charges on both sides should balance. That's a little tricky to use, though, because we didn't write the spectator ion on the right. So if you're going to use that method, you kind of have to ignore the spectator ion unless you're going to draw it on both sides. Okay, so I'm not saying that's the most important technique for doing the charges, but it is a kind of a backup way of checking or kind of alerting you if you've made a mistake. Okay, so we go ahead and change the positive charge back to neutral.
Okay.
Okay. Well, obviously you should be marking all the questions that you missed. You can go back and get them, try them again. Again, the point is, I know that you understand conceptually how to do that, but our goal is to get these right without careless mistakes as well. So that's important to practice. Okay, so I'll take a look at the next problem. Okay, that looks fine. So I'll take a look at the next problem, the bromine. 5 attaches to 1 and 2. Okay, now in this case, you didn't use the positive charge on the nitrogen. You didn't use the positive charge on the nitrogen. But if you remember, we shouldn't worry about that too much because we've seen that when there's 2 formal charges in the same molecule, oftentimes you can only use one of them. So these are reasonable arrows. How many charges should we change on every step of every mechanism?
I didn't write the bromine negative, but...
So let's go ahead and write that in. Now, it's true that oftentimes instructors won't care about that bromine. You wouldn't necessarily lose credit for this, but I think it's a really important, it's a very important habit to always draw both charges that changed so that we're really building that habit. So even though that might not be required by the instructor, I think it's required for us to build good habits. So we should always make sure that we're showing both charges that are changing, even when one of them is kind of on an uninteresting molecule like the bromine. Okay, so continuing, let's look at the next. 2 attaches to 5, which is the OH, 6 and 7. This is another case where you didn't use the positive charge on the left-hand oxygen, but that's okay because oftentimes if there's 2 charges in the same molecule, you can really only use one of them. So that looks like that was correct to me. All right, it's good that you saw the next one was no reaction because what role would the cyanide want to play in a reaction?
Nucleophile.
And what role would the iodide want to play?
Also nucleophile.
Do nucleophiles react with nucleophiles?
Nope.
No. What do nucleophiles react with?
Electrophiles.
So that reaction would be no reaction. Good.
Yeah.
Then the next one, again, you said no reaction. So the left-hand molecule is positive. What type of molecule do positive things want to react with? Positive, positive or negative?
Negative.
Yeah. So generally speaking, 2 positives are not going to have a good reaction between them. And 2 negatives are not going to have a good reaction between them. Remember from chemistry, it's unlike charges that attract. So are these two starting materials going to get close to each other or move away from each other?
Move away.
Well, they can't react with each other if they're not even close to each other, right? Remember that all reactions really mean are things bumping into each other. In order for a reaction to happen, the molecules have to first bump into each other, and these don't want to bump into each other, just like the cyanide and the iodide wouldn't tend to bump into each other. Okay, good. Let's continue. It's good to see when there's no reaction. All right, here we have 8 attached to 2, attached to 1 oxygen. 3, 4, 5, 6, 7, 8, 9. 8. 8 has 9 on it. 5 has 6. Okay, many students have trouble drawing these rings, but I think you've been doing quite well with drawing those. So that looks like that was correct. Good. Good. All right, then the next example. O connected to 2. Two connected to O. Let's see, what am I thinking here? 1 and 3, 2, O, 4, 5. Okay, yes, that is the correct way to draw that. That's good. And then the next example, we haven't done many problems with alkynes. 7. attaches to 3, 2, 1. 7 is attached to 6, 5, 4. So what role is carbon 7 playing?
Nucleophile.
And why is that reasonable?
It has a negative charge.
So notice, even though you and I have really almost seen no examples with alkynes, doesn't matter, you were able to use the general rules to predict what was going to happen here. And you even drew the alkyne as being linear. That's good. People often don't do that, but you drew it as being linear on both sides. That was an extra bit of good answer. Okay, all right. So I think maybe there was one example there that we missed with a careless mistake. So that's pretty good. Our goal is to get as close to 100% accuracy as we can on this. So we're not quite there, but we're certainly well on our way. So I think that's some good progress. So let's look at the next set of homework. Okay. These are more of the same. Let's see. So the first question was designed to test whether you were going to change the charge on the nitrogen to positive, and you did that. So that's good. And you drew the bromine here. That's good as well. Why is carbon-2 a reasonable electrophile?
Because it is partially positive.
Excellent. Good. The next example was designed to test if you would change the charge on the oxygen to a positive, and it looks like you did that. So that's good. SH21. The next example was designed to test if you would remember to change the charge on the sulfur to a positive, and you did. Good. So let's scroll down. 3, 4, 5, 0. All right, so this example was designed to test if you would remember to change the charge on the oxygen to positive, and you did, so that's good. What role is the oxygen with the positive charge playing?
Leaving group.
And why is that reasonable?
It has a positive charge.
That's right, so it's playing the role of a leaving group. Okay. Okay, so previously we had a little trouble with the sodium borohydride reactions, but it looks like this time you've drawn that correctly. Who's the nucleophile here?
The hydrogen.
And why is that?
Because it's attached to the negatively charged boron.
So why isn't the boron the nucleophile?
It already has a full octet. So it wouldn't get rid of its negative charge if we didn't have the hydrogen.
Okay, yes. Why doesn't the boron just... Okay, that you're pretty much on the right track. Basically what we've seen is that when a metal or a semi-metal has a negative charge, it's the attached atom that's the nucleophile. That's the simplest way to think about it. So what you were saying actually is a good explanation. But to simplify, we've seen that normally atoms with negative charges are nucleophiles. But when a metal or a semi-metal has a negative charge, it's the attached atom that's the nucleophile. Okay, what you said wasn't really wrong. Okay, what role is the alcohol playing?
That over there is just a solvent.
Yeah, well, you don't know for sure, but that would be a good guess, and that's correct. It's playing the role of the solvent. How do we know it's not participating in the reaction? Well, we know that we want to use the thing that's charged preferentially. So sodium borohydride is a better thing to use. There's a good reaction between that and the carbonyl. All right, then you have the lithium aluminum hydride. So point to the nucleophile in the next reaction. Good. Who is that hydrogen bonded to?
Oops, I drew that wrong. It should be bonded to the aluminum.
That's right. All right. So sometimes we have to redraw the original molecule a little in order to draw the reaction correctly. So this is another case. Why isn't the aluminum the nucleophile? Because when metals or semi-metals have negative charges, it's the attached atom that's the nucleophile.
Yeah.
Okay. So that gave us trouble before, but it looks like we got those correct this time. So looking at the next example.
So would that also hold true if it's not a hydrogen? Could it be like a carbon or something attached to a metal?
Yes, that's right. So there aren't really that many other examples of that in OChem. There's only one or two other examples. These are by far the most important examples. There are one or two other examples that you will see eventually in the second semester, but these are there's not many examples of this exception. But in general, so you aren't going to see any examples where, well, yeah, I don't think you're going to see any examples where the aluminum or boron is attached to a carbon. But there are some other things that they can be attached to. Just one or two other examples. So that's right. It is a general pattern, although there's not many examples. Okay, so looking at the next example. 1, 2, 3, iodide. All right, so you change the charge on the nitrogen to positive. That's the most important part. Next example. You change the charge on the oxygen to positive. That's the key. Good. Next example. So that next example with the sulfur feels weird to many students, but we just followed the general rules and you got the correct answer. And you remember to change the charge on the sulfur to positive. So that's good. How did you know the sulfur would be a nucleophile?
Because of its electron pair.
That's right.
Lone pair.
You might not have studied sulfur much, but if you see it, you can expect it to be a nucleophile because of the lone pair. All right, next example. Good. Why is carbon-3 a reasonable electrophile?
Because of its partial positive. Well, yeah. Okay.
Point to the example that you're looking at. So I want to make sure we're looking at the same example since I didn't number these. Yeah, that's the one. Okay. So why is carbon-3 a reasonable electrophile?
Well, it's attached to a positively charged atom.
That's what I was going for. Okay. So you were a little stumped there for a second, but that's the right answer. That's just the general pattern. So we don't expect the bromine to be an electrophile. Because remember, atoms with positive charges are usually not electrophiles. They're usually leaving groups. Usually the attached atom is the electrophile. Okay, so that you came up with the right explanation there. That's correct. Let's scroll down. Another example with the sodium borohydride.
Oh, I did that same thing. I got to watch that.
Notice that if you had really drawn, if that was really the bond, you wouldn't have drawn the right products there. So that is important to be a little bit careful with. Okay, so why is the boron not the nucleophile? Because when there's a negative charge on a metal or a semi-metal, it's the attached atom that's the nucleophile. Yeah. There's not that many other examples of that in OChem except besides sodium borohydride and lithium aluminum hydride, but there's one or two others that you'll see later. All right, here's another lithium aluminum hydride. So check the bonds that you drew.
Wow. That's funny that I did that so often. I really gotta.
Okay, so better to be a little bit more careful about that. So you drew the products as if the hydrogen had been bonded to the aluminum. That's true. The hydrogen can't be bonded to another hydrogen because hydrogens can't have two bonds. That wouldn't really make sense. Okay. Notice that this is another reaction where there's a third reagent you didn't use. It's better to use the lithium aluminum hydride than the ether above the arrow because the lithium aluminum hydride is charged. Okay, well, I think you got those 100% correct. That said, no mistakes except for that little issue with the bonds. So that's some important progress. Excuse me. Okay, so that's some good progress on drawing the products, and also some good progress on identifying nucleophiles and electrophiles. So we're certainly ready now. I think that's pretty much in the bag for us right now, as long as you keep reviewing that. So now we can definitely start focusing on the acid-base reactions. So let's move on now to the next set of problems, which are about that. All right, nucleophile donates electrons to join an electrophile. Electrophile receives electrons to join a nucleophile. Leaving group receives electrons to leave. Quote-unquote something. Well put. Acid receives electrons to donate a proton. Base donates electrons to steal a proton. Okay, very good. Now, the hard part is remembering these. I find students have a really hard time remembering these definitions unless I quiz them about them every single session, but they're absolutely crucial to keep remembering. You can't play chess if you keep forgetting what a bishop does, and you can't play organic chemistry if you keep forgetting whether an acid donates and receives electrons. So we have those down now, but we have to keep reviewing them. Good?
Okay.
All right, number 3. So how can you remember that an acid wants to receive electrons if you forget it?
Just remember this H3O plus is a good example of an acid that has a positive charge. So that would naturally want to gain electrons.
Because electrons are negative. Good. And how can you remember that bases want to donate electrons?
Well, if you remember this hydroxide anion, then you would see that it has a negative charge, and it would be wanting to become more positive by donating electrons.
That's right. Now, and why am I giving you these two examples to help you remember what acids and bases are? Because from past experience with past students, I am desperate. I have a heck of a time trying to figure out a way to get people to remember the electron definitions for acids and bases. I've never had much success with that, but I'm hoping this will work. All right, so just to warn you, other students have a really hard time remembering this, and it's very important. So this is hopefully this will be a memory aid that will help us with that. Okay, we certainly seem to have that down now, so what you just said was good. All right, so going on to number 3, atom with a negative formal charge, nucleophile or base. Atom with a positive formal charge. What's one other role that an atom with a positive formal charge could play besides electrophile or acid?
It could play leaving group.
In fact, they usually are leaving groups, right?
Mm-hmm.
In fact, only carbons with positive charges are electrophiles. So a better answer for number 4 would be electrophile or leaving group or acid.
True.
So let's add that there. How can you tell if it will be electrophile or a leaving group? Well, remember, most atoms with positive charges play what role?
Most atoms with positive charge will be a leaving group.
So what types of atoms with positive charges would be electrophiles?
Carbon and
pretty much just carbons.
Yeah.
Although H plus is also kind of an electrophile, although you can really think of it just as an acid. Okay. Okay, good. So the most important aspect of organic chemistry is the charges. We were reviewing that there. Number 5, let's move on. Okay, what makes water a reasonable base?
Its lone pair of electrons.
Good. And what makes it a reasonable acid?
It's hydrogen that could be stolen. The oxygen could retain the electrons, while the proton could be taken by a base. Something that's...
But how do we know that the proton could be stolen? After all, almost all compounds have hydrogens. For example, off to the side, do you know how to draw propane? Draw propane off to the side. Is that a base?
Yeah, I guess it could be.
Okay, really it's not. So this is something we might have forgotten. So remember that the best sign of a base is a negative formal charge. But if there's no negative formal charge, what else can you look for? Remember, you kind of look for, we talked about last time, if there's no formal charges, the way you find acids and bases is kind of similar to how you would find nucleophiles or electrophiles. So the key thing is, what's the delta charge on the hydrogen in water?
Partial positive.
So that's the key, the clue that it's that it's acidic.
Okay.
That's the clue. Did we talk about that last time? I think we talked about that a little last time. So that's what would make it acidic. On the other hand, what's the delta charge on the hydrogens in propane?
There is no delta charge.
That's why they're not acidic. Okay, so you can't just assume that just because there's hydrogens, it's acidic. We can't assume that just because there's hydrogens, it's acidic. You have to look for that delta positive charge. All right, what makes the potassium hydroxide basic?
Because of the ionic bond leaves oxygen with a negative charge.
Right. And something with a negative charge could never be acidic. Okay. What makes the H3O plus acidic?
Because of its positive charge.
Something with a positive charge could never be basic. What makes the alcohol basic?
It has a lone pair on the oxygen.
Good. And what makes the alcohol acidic?
I guess it does have a partial positive charge on that proton.
That's what makes it acidic. Yes, you might not have thought about that. Oh, you didn't say it was acidic, did you?
I didn't, yes.
So that's true. It's both a weak acid and a weak base. Do you see how similar the alcohol is to water?
Yeah, actually.
So water and alcohol are very similar in their properties. So we should mark we actually got that one incorrect. There's many examples where alcohols act as weak acids. Okay. All right. So moving on. The next one is clearly basic because of the negative charge.
Yeah.
Now this next example, why did you say the alcohol was basic?
Because of a lone pair.
On the oxygen, yeah.
On the oxygen, yeah.
So I think you need to rethink the nitrogen example now.
Yeah. Looks like it could be either.
Yes.
Or both.
Why could it be basic?
Basic because of its lone pair.
On the nitrogen, yeah.
On the nitrogen,
And why did you say it could be acidic?
It could be acidic because of its partial positive charge.
That's right. It's actually a very, very weak acid. That doesn't come up much in OChem. It's not very acidic. But technically, it's both a weak acid and a weak base. Okay. The next one is clearly basic because of the negative formal charge. The next example, lithium aluminum hydride, looks like it's basic because, again, of the negative formal charge. Clearly, H plus looks acidic because of the positive formal charge. Why is the sodium hydride basic?
Because of its negative charge.
That's right. I think I might have mentioned last time, people oftentimes confuse the sodium hydride with the example in front of it. People confuse the H plus with the NaH. But we've seen hydrogens can be either acidic or basic, depending on their charge. The most important factor in organic chemistry is the charges. The next example is basic because of the negative charge. And then this next example is a little bit tricky. So technically, what makes this, who would be the basic atom here?
This carbon.
Yeah.
Right.
Any particular reason that makes it basic?
Because of its partial negative charge.
Excellent. That's right. That's right. Although you might also remember that alkyl lithiums can also be written ionically. And if we wrote it ionically, then we'd have even better reason to think that it was basic. But even in this picture, it has a delta negative, which tends to make it basic. Okay, so we missed a couple of the weak acids and weak bases there. In particular, the fact that the NH2 up above was basic is actually quite important. It's not a very strong acid, but the fact that it's basic is pretty important. Okay, let me go back to my screen.
Okay. I don't know.
Oh, no, actually, let's stay on your screen and look at the rest of the problems.
Okay. A couple of these I was not totally sure on. So.
Okay, HCl is an acid. You might just have memorized that it's an acid. Can you think of any reason why it's reason that's reasonable to think of it as an acid?
Well, the hydrogen would have a partial charge on it.
That's what makes it an acidic proton. Yes. All right. Then the next example. Who's the basic atom in the next example?
The oxygen.
And why is that?
Because of its lone pair.
Excellent. But then if you give it a positive charge, it becomes acidic. Now, why did you say that the next example was basic with the ring?
Well, okay. I was looking at alkene. And that could work as a base.
Good. So remember we said that the things that tend to make things nucleophilic tend to also make things basic.
Yeah.
And the things that tend to make things electrophilic also tend to make things acidic. The rules are pretty similar. Do you have the handout with you?
Yeah, I do.
So, on the first page of the handout, I kind of grouped bases together with nucleophiles because the clues are similar for both of them. And I grouped electrophiles together with acids because the clues are similar to both of them. That's good, so we don't have to memorize a bunch of new stuff. Then the next example with the three-membered ring is basic because of the lone pair. So let's scroll down.
Yeah.
Then the next example is acidic because of the positive charge. Then the next example is acidic because of the positive charge. Then the next example is basic because of the lone pair. Who's the basic atom in the Grignard reagent?
The second carbon.
And why is that reasonable?
Because of its partial negative charge.
Excellent. That's a good answer. That's right. Also, if we had drawn it, we could have drawn it ionically bonded, and then it would have a full negative. But even in this picture, it has a delta negative. So your answer was correct. Your answer was correct. Now I notice who's the basic atom in this next compound with the nitrogen?
The nitrogen.
And why is that reasonable?
Its lone pair of electrons.
That's good that you saw that. Yeah. And then, but if it's so notice that there's something. I should have been pointing this out more clearly. Notice that if we protonate the nitrogen, now it's acidic because of the positive charge. So notice that the same compound can switch from acid to base. The same compound can switch from acid to base. I meant to point that out before. Look at the two compounds before the Grignard up above. Do you see how those two compounds are almost the same thing?
Yeah.
One is the top one is just the protonated version of the bottom one. So that shows you that something can easily shift from acid to base depending on whether it's protonated or not. Actually, there's a bunch of examples like that here. Okay, so let's scroll down. So then the S minus is a base because of the negative. Let's see. And then the SH, why is, so now the SH, why would you say that that's basic?
Well, I was seeing that because of a lone pair on sulfur.
Excellent, that's true. Could it play any other roles?
Looks like it could also play the role of an acid because of the delta positive charge on hydrogen.
That's right. So really that one should be both possibly basic or acidic, depending on conditions. Notice that that's actually pretty similar to an alcohol. So it's not surprising it plays a similar role. Now the next example, could the next example be acidic?
No, it would just be basic.
Because the only hydrogens are on the carbons. And what's the delta charge of the hydrogens on the carbons?
There is no delta charge on them.
That's why we don't even usually bother drawing them. So that is only basic. And then the next example is acidic. So do you see the kind of the theme in the last four examples? I was trying to show how very similar compounds could play quite different roles. So if you basically make changes in how protonated they are. So that's kind of the lesson of these problems. Depending on how protonated the compound is, the sulfur is, or basically the element can play different roles. Sulfur can play many different roles depending on its charge and how protonated it is. HBr, what makes the H there acidic?
The delta positive charge on the hydrogen.
Okay, so there was a couple there that you missed. I think you hadn't quite remembered from the previous session the idea that the clues for acids and bases are quite similar to the clues for electrophiles and nucleophiles. So delta positive, hydrogens with delta positive charges tend to be acidic, for example. Is an important idea that we weren't quite using on a couple of those problems. Okay, so let's go back to my screen. Overall, that was pretty good execution on those problems. So so that's good that you took the time to do all of those. That's good. So that's some good work. Okay, so let's take a look here. So what roles might you expect this compound to play in a reaction?
It could be... Well,
let's just focus on acid and base.
Acid and base, okay. So it could be both acid or base. Could be an acid because of the delta positive charge on hydrogen, and it could be a base from a lone pair of electrons on nitrogen.
Good. Now, I should warn you, all of these rules are just rules of thumb. This is actually a very weak acid. There's not many examples in OChem where it really would be acidic, this particular compound with a nitrogen. But it does follow the rules that we were talking about. So you should keep in mind, all of these rules we were talking about, they're just rules of thumb. As you study more and more OChem, you'll learn more exceptions to them. So nitrogens with hydrogens are actually only very weak acids. There's not many examples in OChem where they're acidic, but it does meet the qualifications based on what I talked to you about so far. Okay, good. So, okay, let's continue. Let's see. So the next thing we have to discuss is, I'm sure you've heard that this is not a democracy. Not all acids and bases are created equal. So there are strong acids and there are weak acids. And there are strong bases and there are weak bases. Well, what's the definition of an acid?
An acid will lose a proton and receive electrons.
Very good. Good. So what's the difference between a strong acid and a weak acid? Well, I'll just tell you. As far as our purposes, we can just say strong acids are more eager to donate protons and receive electrons, and weaker acids are less eager to donate protons and receive electrons. So who's more reactive, a strong acid or a weak acid?
Strong acid.
Okay. So what do you think is the difference between a strong base and a weak base?
Its eagerness to donate electrons, perhaps, would be an indicator of how eager I guess the more eager it is to donate electrons, the stronger the base would be.
That's right. Or the more eager it is to steal a proton, you could say, the stronger the base would be.
Okay.
Which of these four reactions is most likely to actually happen? And which of these four reactions is most likely to be no reaction?
Seems like a strong acid and a strong base would be most reactive.
And which reaction is likely to be no reaction?
When they're both weak.
Good. Now, this would have been hard to predict, but it turns out that in organic chemistry, these reactions generally happen as well. So this is an important principle. Just because you have an acid and a base doesn't mean you're going to have an acid-base reaction. A weak acid does not do an acid-base reaction with a weak base.
Okay.
So here we would have an acid-base reaction. And here we would have an acid-base reaction. And here we would have an acid-base reaction. I shouldn't have said no reaction here. I should have said no acid-base reaction. There might be a different type of reaction, but there wouldn't be an acid-base reaction here.
Okay.
Okay. So can you have an acid-base reaction between a strong acid and a weak base?
Yeah.
Can you have, yes. Can you have an acid-base reaction between a weak acid and a strong base?
Yeah. Or between a weak acid
and a strong base.
Yes, you can.
Yes. Can you have an acid-base reaction between a weak acid and a weak base?
No, there wouldn't be an acid-base reaction.
That's right. Okay. By the way, even though you could have an acid-base reaction between a strong acid and a strong base, that almost never happens in organic chemistry. In organic chemistry, these are the reactions that you'll usually see.
Okay.
This is theoretically possible, but it just doesn't come up much in an OChem course. This is theoretically possible, but doesn't come up much in OChem. If it did come up, you would get the acid-base reaction, but this is what you're usually going to see. These two. You wouldn't get an acid-base reaction here. Okay. Now, this is not going to be very useful to us unless you can tell whether something is a strong acid or a weak acid, or a strong base or a weak base. So now we need to go over the rules so we can tell the difference between them. So first of all, what type of charge would make you an acidic?
Positive.
So pretty much anything with a positive formal charge is a strong acid.
Okay.
Anything with a positive formal charge would be a strong acid. And there's 4 things that are neutral, that are strong acids. There's 4 neutral molecules that are strong acids. Do you know any neutral molecules that are strong acids? You should have seen some of these in just general chemistry courses. Can you think of any neutral molecules that are strong acids? Can you think of a strong acid?
Maybe chlorine attached with hydrogen?
That's right. That's hydrochloric acid. That might be the most famous acid.
Okay.
Hydrochloric acid is a strong acid, even though what's the formal charge in hydrochloric acid?
It's neutral.
But it is a strong acid. Okay. I don't know. Can you think of any other strong acids that are neutral?
Perhaps bromine. I'm not sure if that would be a strong one. Bromine and hydrogen.
That's true. And this one is also a strong acid. Shouldn't surprise us because they're all in the same column.
Yeah.
By the way, this is not a strong acid, even though it's in the same column.
Okay.
We don't really use fluorine much in organic chemistry anyway, so this wouldn't generally come up much, but this is not a strong acid. By the way, the name of this is hydrochloric acid. This is hydrobromic acid and hydroiodic acid.
Okay.
There isn't one more that I think you've probably seen. Do you know what the name of this compound is?
Is it sulfuric acid or?
Yeah, it's sulfuric acid. That's certainly another very famous strong acid, even though it's neutral. All right, these are the only neutral compounds that are strong acids in organic chemistry. These are the only neutral compounds that are strong acids. There are other strong acids, but they don't come up much in organic chemistry. So these are the only strong acids that are neutral that play a significant role in an introductory organic chemistry class. So I'll just make this list. Okay. So what type of acid is this?
Hydrochloric. It's strong acid.
What type of acid is this?
A weak acid.
Because it's neutral, but it's not in our list.
Yeah.
What type of acid is this?
It'd be a strong acid.
Because it's got a positive charge. Notice it's just the protonated form of the alcohol. Good? What type of acid is this?
Also a strong acid.
Because it's protonated.
Yeah. So I guess that weak acid that has the alcohol, it does have a hydrogen on there, but you don't term it as being protonated, right?
Oh, that's a good point. Yeah, well, and of course it's got protons all over the place. So yeah, usually we say something is protonated when it has more hydrogens than usual.
Okay.
So you don't usually talk about a neutral compound as being protonated. Okay. So this is what's called a protonated alcohol. But yeah, that's right, it's a little bit ambiguous. So being protonated doesn't just mean you have a proton, it means you have more protons than usual. Okay. What type of acid is this?
Strong.
Because we just memorized that that's a neutral strong acid.
Yeah.
Okay, so that's how we apply those rules. Now, how about strong bases? Unfortunately, this is trickier because not everything... So if something has a negative charge, does it tend to be an acid or a base?
Base.
But not everything with a negative formal charge is a strong base. Some things with negative formal charges are still only weak bases, unfortunately. So I'll just write down O- is a strong base. N- is a strong base. And then I'll just write down some other strong bases. This is a strong base. This is a strong base. What type of compound is this?
Grignard.
That's a strong base. Remember, we called these alkyl lithiums. They're like Grignards. They're strong bases. I think that's it.
Okay.
I don't think anything neutral is a strong base, except Grignards and alkyl lithiums are sometimes drawn as neutral. but nothing else that's neutral. So these are the only strong bases that I can think of right now. These are the strong bases in organic chemistry. Obviously, there's other strong bases in the universe, but these are the ones you're going to see in an introductory OChem class. Okay.
Okay.
Okay, so for each of the next examples, we're going to try to classify, is it strong acid, weak acid, strong base, or weak base, and it might be both acid and base, remember, so it can be tricky.
Okay.
So let's try a bunch of these. How about this one?
That would be a strong base.
Because of the O minus.
Yeah.
How about this?
That could be both. Could be a weak acid because of the delta positive charge on the hydrogen, and it could be a weak base because of the lone pair of electrons on the oxygen.
Good. Notice the only way you can play both roles is if you're weak in both of them. There's no way a strong base could also be acidic. And there's no way that a strong acid could also be basic. The only things that could play both acid and base roles are the weak things. Good?
Oh.
How about this?
That could play both weak acid and weak base. Acid because of the positively or partially positively charged hydrogen, and the lone pair on the oxygen could make it a weak base.
Good. How about this?
That would be a strong base because of the positively charged oxygen.
Negatively charged oxygen.
Ah,
Good.
thanks. Sorry.
All right. How about this?
That could play the role of either weak base or weak acid.
Yeah, it's actually a very, very weak acid, but technically it falls into the weak acid category too. Good.
So it would actually play a better base than it would acid.
I would say it's more like it's very commonly used in OChem as a weak base.
Okay.
It's very rarely used as a weak acid because it's so weak. It does, unfortunately. So remember, all our rules have exceptions. So it is this. Let me just put it this way. Let's not beat around the bush here. Why did you say that this was acidic?
Because of the delta positive charge on hydrogen.
How do you know there's a delta positive?
Because O is electronegative, it would have a delta negative charge on it.
How do you know that the oxygen is more electronegative than the hydrogen?
It's further out to the right on the...
And how do you know that this is acidic?
The delta positive charge on the hydrogen.
Who's got a bigger delta positive? Which of these hydrogens? On the oxygen or on the nitrogen?
Oxygen.
Why?
Oxygen is further to the right on the periodic table than the nitrogen.
Right. Remember, hydrogen is similar to what element in electronegativity?
Carbon.
Right. And so where is nitrogen compared to carbon in the periodic table? Far to the right or close to the right?
Close to the right.
In fact, it's right next door, right? It's only one element over. So is there a big or small electronegativity difference here?
Very small.
Yeah. So actually, that explains why I keep kind of hedging my bets here. Technically, this is acidic, but actually the delta positive is pretty darn small. So it's not really all that acidic. Okay. So hopefully that makes it clear. So technically, it falls into the weak acid category, but there's not many reactions in OChem where it would actually be acidic.
Okay.
All right. Because even though it is delta positive, it's a very small delta positive. All right.
Okay.
We won't worry about that too much right now, though. So for that reason, I'll go ahead and cross this out. It doesn't play a role of an acid much in OChem. Okay. So because the delta positive is there, but actually quite small. All right. What role would this? Whoops. What role would this play?
base.
Good.
Because
Remember, our goal here is also to classify as strong or weak.
oh, that's right. Strong. It has a negative charge on the nitrogen.
How about this?
Also a strong base.
Now this one we got tripped up on. Remember that bases are a little bit tricky. Where's my notes? Anything with a positive formal charge is a strong acid, but not everything with a negative formal charge is a strong base.
Right.
Only these things. These are the only strong bases. These are the only strong bases. That's a little bit tricky here. So let's rethink your answer here. What's the answer to this one?
That would be a weak base.
That's right, despite the negative charge. So we need to memorize. Maybe I should have given you a little more second. Take a few seconds to try to memorize this list. This is the list of the strong bases. Anything not in this list is probably not going to be a strong base. Tell me when you feel you kind of have that down.
Okay, I think I'll remember it just by remembering either the word on or no with the negative.
Good.
And
Good.
then anything that could be shown as having an ionic bond.
Let's see. Well, that's not quite right. Maybe you're thinking of the right thing, but what role would this play?
Huh. Oh, okay. Well, I guess it would still be a weak base.
Because again, it's got a negative charge, but it's not in that list. So we just have to memorize the list. These are the things that are strong bases. Other things are not strong bases, even if they have negative formal charges.
Okay. So I did notice that I can't think of the name of it, but the lithium aluminum hydride, that would be considered a strong base, but the boron, if that were to take the place of aluminum, would not necessarily be a strong base. Is that right?
That's a good thing that you noticed that. That is true. That is true. Sodium borohydride is only a weak base. That turns out to play a role in how we set up reactions in OChem. So that's an important difference between those. Sodium borohydride is only a weak base. Maybe
Okay.
let me add maybe this as well.
Okay.
If this came up, this would be a strong base. Okay. How about this?
That would be a strong base. Because it's... No. Okay, sorry, I was mixing that up. A neutral halogen the hydrogen on a neutral halogen can be acidic, but this would be a weak base.
Right. In fact, it's very weak. We haven't talked about this much yet, but have you ever heard the idea that the conjugate of a strong acid is a weak base?
Yeah.
In fact, the stronger the acid, the weaker its conjugate base. That's a better way of putting it. The stronger the acid, the weaker its conjugate base. Have you heard that idea?
Yeah, I have.
Well, we know that HCl is a very strong acid. So in fact, this is a very, very weak base.
Okay.
Hardly basic at all, actually. The important thing is it's certainly not a strong base, even though it has a negative charge. The important lesson here is we're trying to learn negative charges don't guarantee that you're a strong base. Negative charges don't guarantee a strong base. Maybe let's just take a second. I went through this a little bit quickly. Take maybe a few more seconds. We just need to basically memorize this table. This is the table. Anything that's not in this table is not a strong acid or a strong base. So rather than relying on rules here, we're just kind of memorizing the table. So take a few more seconds. Tell me when you feel that you've just basically memorized both sides of the table.
Okay.
How about this?
Strong acid.
Because we memorized that it's a strong acid. Good.
Yeah.
How about this?
Also, well, yeah, also a strong acid. Has a
Anything with a positive formal charge is a strong acid. How about this?
That could play the role of a weak base.
Good. Who could be the basic atom?
Either oxygen.
Either. That's right. Either could be a weak base. How about this?
That could be a strong acid because of the positive charge.
So who would be the acidic atom?
The oxygen with positive?
Not this one. Good.
Yeah. Protonated, yeah.
The protonated oxygen. Yes. So what role could this play?
Strong acid for the same reason on the protonated oxygen.
Good. How about this?
It wouldn't likely play the role of a weak acid, but it could play the role of a weak base.
We discussed that. Even the delta positive is pretty small, so it would probably be a weak base. Good. How about this?
Huh. That would be a strong acid. That's one that we memorized. An N with a negative charge. Strong base, sorry. Strong base.
N with negative formal charges are strong bases. Good.
Yeah.
How about this?
Also a strong base, because it's a Grignard.
And we memorized that those are strong bases. Good.
Yeah.
Who would be the basic atom?
Carbon 2.
Good. How about this?
Also strong base, carbon 2. It's one that we memorized.
Good.
Lithium, alkyl lithium.
How about this?
That's also a strong base. Lithium, aluminum.
Because we memorized that.
Yeah.
How about this?
That would be a weak base.
Because it has a negative formal charge.
Right.
Who would be the basic atom here?
The hydrogen attached to boron, one of the hydrogens.
Yeah, because we know that when there's a negative charge on a metal or a semi-metal, it's the attached atom that is the nucleophile or the base. Good.
Yeah.
So these are some important compounds here. Good. Let's see. Okay, I think we're getting the idea there. Good. Could there be an acid-base reaction here?
Yeah.
What role would this play?
That would be the acid.
Weak or strong?
Weak acid.
And what role would this play?
Strong base.
Good. Could there be an acid-base reaction here?
No, they would. Well, there could be. Could be weak acid, weak base reaction. I guess no. We said that doesn't cause a reaction. Okay, so no, there would not be a reaction, an acid-base reaction.
Okay, you had to think about that for a little bit, but you ended up with the right answer. So we hadn't talked about that for a few minutes, but then you remembered. So what I wanted to test here was this idea here, this table. remember, it's not enough to see that there's an acid and a base. If they're both weak, you still won't get an acid-base reaction.
Okay.
So you did end up with the right answer. So it's important to compare these two examples. These seem very similar, but there's a huge difference in the reactivity. And the main thing that makes the difference, why does this oxygen behave differently than this oxygen? Because this oxygen has a negative formal charge. The most important factor in organic chemistry is the charges. Okay, good. Would there be an acid-base reaction here?
No, they're both weak, acid and base.
Would there be an acid-base reaction here?
Yeah, there's a strong acid, H3O plus, and a weak base with the carbonyl.
That's right. So a lot of people get confused between these two cases. They seem very similar, but there's a huge difference because here the oxygen has a positive formal charge. Good. Would there be an acid-base reaction here?
No.
Could there be an acid-base reaction here?
Yeah, there would be strong acid, hydrochloric acid.
And what role would this play?
This would play a weak base.
Okay, good. Could there be an acid-base reaction here?
Yeah.
What role would this play?
Strong base.
And this?
A weak acid.
Could there be an acid-base reaction here?
No, they're both weak.
That's right, they're both weak. We saw that's a difference between lithium aluminum hydride and sodium borohydride. Would there be an acid-base reaction here?
Yes.
So what role would this play?
Strong acid.
And this?
A weak base.
Could there be an acid-base reaction here?
Yeah, the alkyl lithium is a strong acid. The alcohol would be a weak base.
Okay. What role could this play in the reaction? Acid, base, nucleophile, or electrophile?
Seems like it's most commonly an electrophile. Carbon-2 would be. But I think it could play the role of any of them. It could be a base because of the lone pair on the oxygen.
Strong or weak?
It would be weak. It doesn't have a negative charge on it, so it'd be a weak base. And it could be... I wonder if it... Well, it does have a lone pair on the oxygen. Could it play the role of nucleophile because of that?
That certainly would make sense, yes. According to our rules, it could play the role of a nucleophile. That's a good point. What's the name of this type of functional group? A carbon double bonded to an oxygen?
Carbonyl.
All right. I'm just going to tell you, as a new extra rule to load you down with, carbonyl oxygens usually aren't nucleophiles, even though they have lone pairs. Okay. So, according to our rules, you would expect that the carbonyl oxygen could be a nucleophile. That was good that you thought about that. But I'll just tell you as a little extra rule or exception, usually carbonyl oxygens do not play the role of a nucleophile, at least not in the intro course.
Okay.
Okay. I don't think we would expect this to play the role of an acid. Anyway, my point was there's two different roles it could play.
Yeah, did we? It seems like one of the sample problems on the left, we did have that same molecule be an acid.
I think it probably looked like this then.
Could have been. Yeah, trying to remember.
So here's the one that was the acid. I didn't really, oh, here we go. So here we had this, we just said weak base.
Okay.
We didn't say acid. Yeah.
Okay, yeah, thanks for clarifying that.
Okay, so I don't think we had it play the role of an acid in any of those. Okay, hopefully not. All right. What role can this play in a reaction?
That would be a strong base.
Any other roles it can play? Now let's start. So what I want to start doing now is putting together the nucleophile electrophile material with the acid-base material. I think we've made some good progress on acid bases by themselves, so now we have to start integrating things together and thinking about them all simultaneously. So any other roles besides acid and base this could play?
Okay, so yeah, it could be a nucleophile as well.
We've seen many examples that Grignards can play the role of a nucleophile. Good?
Yeah.
What roles might we expect this to play?
Strong acid or a... Sorry, I said that wrong. Strong base is what I meant to say, and a nucleophile.
Good. What roles could we expect this to play?
That could be a strong acid, and it could also be an electrophile.
Okay, so we should maybe be starting to feel a little discouraged here, because how do we know? It would be nicer if they can only play one role, right? It's a little discouraging that there's multiple roles they can play, because we want to know which one it's going to be. So this is one of the challenging parts of organic chemistry that gives people a lot of trouble. They don't know when to do nucleophile. So basically we can say that most reactions in organic chemistry, there's two basic types of reactions. There's nucleophile, electrophile reactions, and there's acid-base reactions. Most reactions, not all reactions, but most reactions fall into one of these categories. So usually what you need to do, remember that our goal here is to be able to predict the electron-pushing arrows on our own. Our goal here is to be able to predict the electron-pushing arrows on our own. Well, it's a little discouraging because how can you tell? Are we going to have a nucleophile-electrophile reaction or an acid-base reaction? It can sometimes be difficult to tell. Well, that's our next task. Our next task is to start trying to be able to tell the difference, which one we're going to have. Well, first of all, here's the basic pattern in organic chemistry. The basic pattern is that you'll do a nucleophile-electrophile reaction. Then you'll do an acid-base reaction. Then you'll do a nucleophile-electrophile reaction. Then you do an acid-base reaction. then you do a nucleophile electrophile reaction, then you do an acid-base reaction. So the point is, the general pattern is to alternate.
Okay.
The general pattern is to alternate between one, then the other, then the other. Okay. This is something a lot of students don't realize, but this is the pattern in organic chemistry, shifting from one to the other. So that's one strong clue. If you just did a nucleophile electrophile reaction, oftentimes next you should do acid-base. Or if you just did acid-base, oftentimes next you should do nucleophile electrophile. You should keep in mind there's definitely exceptions. This is not a hard and fast rule, it's just a rule of thumb. So there are exceptions that you'll have to learn about as you go, but when in doubt, this is a good rule of thumb. All right, so there's a couple of concerns that you should have here. One concern you should be wondering about is, how do you know when to stop? You got to know when to stop. Did you ever hear the joke about someone asked a kid, how do you spell banana? You ever hear that joke? So the kid said, B-A-N-A-N-A-N-A-N-A-N-A. Well, I know how to spell it, but I don't know when to stop. So it's the same deal here. We know kind of how to do these reactions, but how do you know when to stop? Well, here's the basic clue. You usually stop when the main molecule has no formal charge. That should make sense, because does nature like charges?
Nope.
So as long as the main molecule has a charge, nature wants you to keep going to get rid of that charge.
Yeah.
Now, you should notice this is kind of a vague rule. What the heck does main molecule mean? It's not a hard and fast thing. So you oftentimes can't get rid of all the charges. Oftentimes you can't get rid of all the charges, but you usually can stop when the main molecule has gotten rid of the charge. This is just a useful problem-solving technique for solving problems. Well, the main molecule is usually the bigger one, and it's usually the one that has carbons. So if a molecule doesn't have carbons, so for example, we would not consider this the main molecule because there's no carbons in it. So it's usually the large carbon-containing compound.
Okay.
But in general, the main molecule is the molecule that you're kind of focusing on in the problem. We can't give it a very hard and fast definition. So that's an important rule that we'll use as a kind of clue. Again, this is not always true. There's some exceptions to this. There's some exceptions. That's why I said usually. It's just the general rule. And also there's something else that should have concerned you when I told you about this pattern of alternating. The other thing you should have been wondering is, which one do you do first? Do we start with a nucleophile electrophile reaction, or do we start with acid-base? And that can be pretty tricky. Sometimes it's hard to predict, but I can give you a few rules for that as well. Let's see. If there's a strong acid, you almost always start with an acid-base reaction. That's a nice, simple rule. This is a very good rule because there's almost no exceptions to this. So if there's a strong acid with almost no exceptions, you're going to start with an acid-base reaction. Okay. Unfortunately, strong bases are trickier. Bases can be trickier. So let's see. If you have... I'm going to write down a bunch of rules. I wouldn't expect you to memorize all of the remaining rules right away. It's a little tricky, but I guess it's better to write them down than not to. if you have these two strong bases, you almost always start with an acid-base reaction.
Okay.
If you have these, you will start with an acid-base reaction if there's if there's an acid around. A lot of the time, you keep these away from acids, because what other role does lithium aluminum hydride play besides base?
Nucleophile.
And that's usually what we want it to do. These are designed to be used as nucleophiles. If they were in the presence of a weak acid, they would act as bases. But usually you try to keep them away from acids. If you keep them away from acids, then they can act like nucleophiles. So usually you try to set up the reaction so there's no acid so they can act like nucleophiles. But if you screw up and you put them with an acid, then they would give you an acid-base reaction.
Okay.
Now, O- is the trickiest of all. It can go either way.
Okay.
You just have to learn the details of each particular type of reaction as the course goes on. Sometimes when you have an O-, you start with an acid-base reaction. Sometimes when you have an O-, you start with a nucleophile electrophile reaction. It can go either way. You kind of have to memorize them all as you go along. Let's see. Any other strong bases I didn't remember here? So you can see the bases are kind of confusing. Okay. Otherwise, we start with a nucleophile electrophile reaction. Okay, unfortunately this is a little bit complicated. I wouldn't expect you to have this all quite memorized quite yet. I would especially focus on this we should memorize now. This is a very simple This is a very simple hard and fast rule. If there's a strong acid, you definitely start with an acid-base reaction. If there's a strong acid, you definitely start with an acid-base reaction. But bases are kind of confusing, unfortunately. Bases can kind of go either way. Maybe it's good to go. So some of these can kind of go either way depending on the conditions. But if there's a strong acid, you definitely start with an acid-base reaction. Okay, do you have that in your notes?
Yeah.
Okay, as we go along, this might be a little confusing right now, but I think we'll be able to clarify it as we go. Okay, let's try this on your screen. I'd like you to try to come up with some reasonable arrows for this reaction.
Okay.
And let's draw the product. So is this a nucleophile electrophile reaction or acid-base?
A nucleophile electrophile reaction.
Great. Does it look like we're done, or does it look like we need another step?
Looks like we're done.
How can you tell that we should stop now?
The main molecule looks like it does not have any charge on it.
That's right. Now, do you see what I meant when I said you can't always get rid of all the charges? The iodide still has a charge, But I don't think most people would think of that as the main molecule because it's smaller and because it has no carbons. So
Yeah.
we can stop here. We're done with that reaction. All right, well, that wasn't super hard, but that was good. I'll go back to my screen. Now let's try this example. So again, try to come up with some reasonable arrows and then draw the product.
Okay.
Excellent. So did you do nucleophile, electrophile, or acid-base?
Nucleophile, electrophile.
Great. So does it look like we're done, or do we need another step?
Looks like we could use another step.
Yeah, that's right. How can you tell we're probably not done?
The main molecule has a positive charge.
That usually means we're not done yet. Okay. Well, what should we probably do next? Nucleophile, electrophile, or acid-base?
Probably acid-base.
Because remember, we're supposed to usually alternate, right?
Yeah.
We just did nucleophile, electrophile, so probably it's time for an acid-base reaction. Okay, see if you can come up with a reasonable acid-base reaction here.
Okay.
That's excellent. Now, is the iodide, what role is the iodide playing?
Base.
Good. Is it strong or weak?
It is a weak base.
So will this reaction really happen? What role is the nitrogen playing?
Weak acid. Or, yeah.
So is the nitrogen
No,
a
sorry,
weak acid or a strong acid?
Positive, yeah. So it'd be a strong acid.
Remember, anything with a positive charge is a strong acid. It's a little confusing. I kind of put a whole bunch of rules on you at once. But not everything with a negative charge is a strong base. But everything with a positive charge is a strong acid.
True.
So is this a reasonable reaction?
Yeah.
Yeah. On the other hand, though, do you remember we said that HI is a really strong acid, right?
Yes.
And remember that the stronger the acid, the weaker the conjugate base. So some instructors wouldn't be too happy with this. The iodide is actually a very, very weak base. Some instructors would let you do this. Some instructors wouldn't be too happy with it. So instead, let's just use another of the original 4 or 5 NH2 molecules as the base. Because remember, we haven't used them all up. We've only used up one so far, right? We drew one, but there's still more floating around. So most instructors would prefer that you went back and used more of that 4 or 5 NH2 instead of the I-. Even though I- has a negative charge, because it's the conjugate of a really strong acid, it's not really it's a pretty lousy base. So let's draw another example of the 4 or 5 NH2 and use that as the base.
Okay.
Okay, great. Let's draw the product from that step.
I guess that's a spectator, so
At this point, the iodide is a spectator, so you don't need to keep drawing it. In fact, maybe it's better not to since it didn't participate. Okay, now does it look like we're done or that we need another step?
I mean, I think we're done because looks like our main molecule does not have a charge.
That's right. Do you see why I use that vague term main molecule? There is one molecule here with a charge, and it does have carbons, but hopefully you kind of have the feel that's probably not the main molecule that we're trying to predict what it's going to turn into in this reaction. It's just kind of like a helper molecule that took off that proton. The molecule that's giving us the interesting product is the one up above. So as a problem-solving technique, it looks like we're probably done. Our main molecule no longer has a charge. Okay. All right, well, notice I think we just did now 2 steps here. So that's how we work out those types of steps. Good. I'll go back to my screen.
Okay.
Try to come up with some reasonable arrows here.
Mm.
Great. So what type of reaction did you do first? Nucleophile, electrophile, or acid-base?
Acid-base.
Good. Now that's not what we did in the last 2 problems. How did you know to shift gears here? How did we know that it was almost guaranteed here that we had to start with acid-base?
We had a strong acid here.
That's right. I'll go back to my screen for a second. Remember, I was admitting that these rules are a little complicated, but one rule that's very simple, anytime you have a strong acid, you start with an acid-base reaction. Anytime you have a strong acid, you start with an acid-base reaction. That rule, fortunately, is not very complicated, and there's almost no exceptions to it. I'll go back to your screen. So does it look like we're done?
No.
Why not?
There's still a positive charge on the main molecule.
That's right. So try to come up. What type of reaction should we probably do next? Acid-base or nucleophile electrophile?
Probably a nucleophile electrophile.
Because we just did acid-base. Remember that we usually alternate. So let's try coming up with a reasonable reaction.
Okay.
Okay, that does seem reasonable. That does seem reasonable. What role did you have the oxygen playing? I mean the neutral oxygen.
Nucleophile.
That's right. And why is that reasonable?
Lone pair of electrons that it has.
Okay. Okay. So that's good thinking. That's good thinking. We used up an alcohol in the first step, but that doesn't mean we don't have more alcohol molecules.
Mm-hmm.
But do you see any other atoms floating around that might be reasonable nucleophiles?
The iodine.
Yeah. What makes it a reasonable nucleophile?
Negative charge.
So, in fact, because of that negative charge, it is a much better nucleophile than the alcohol.
Okay.
The iodide is a much better nucleophile than the alcohol. So why did you ignore it? Why did you use a neutral atom instead? Well, I think you might have been remembering that we said earlier, iodide is a very, very bad base, right?
Yeah.
Because it's the conjugate of Hi. But that doesn't mean it can't be a good nucleophile. Those things often go together, but they're not always parallel. It's possible to be a good nucleophile, but not a great base. Let me switch to my screen for a second. This is an important idea. we should just memorize this.
Okay.
Oftentimes, good bases are often also good nucleophiles, but they don't always go together. These are excellent nucleophiles, but they're not very good bases. Some instructors would prefer you pretty much never to use these as bases. Other instructors use them sometimes. So they are bases, but kind of just barely. Because remember, they're the conjugates of really strong acids. So we would expect them to be really, really poor bases. That's probably not obvious, though, so maybe we should just memorize. Because these certainly come up a lot in OChem, right? So we should just kind of memorize that. If you have a choice of using these as a nucleophile, you generally should do that. They're certainly better nucleophiles than a neutral oxygen. Okay, so let's go back to your screen and try that reaction a different way. Good, that's what I was going for. So then let's draw the product.
Oh, sorry.
Okay, so does it look like we're done or we need another step?
Looks like we're done.
How can you tell?
The main molecule has no more charge.
Okay, good. Good. Let's scroll up or maybe zoom out so we can look at the last three problems. I tried to get them all on the screen. Good. I don't know if you remember. Do you know what the name of this what the name of the mechanism is in the first reaction? We haven't really been talking about names of reactions, but that's one of the most important reactions from the first semester. Do you know what the name of that reaction is?
Is that like elimination or substitution?
Right, yeah, to be particular, it's SN2. If you remember that, that's maybe the most important reaction in organic chemistry. So that first reaction is SN2. Actually, these were all SN2. But the difference is the first reaction was just SN2. Whereas in the next, how many steps were there in the second reaction?
2.
First, we did an SN2. Do you see how the first step of the second reaction is pretty similar to the first reaction? So in the second reaction, we did SN2, and then we did an acid-base reaction. So sometimes SN2 is followed by an acid-base reaction. And then look at the third reaction. In that case, first we did an acid-base reaction, and then do you see how the second step of the third reaction is an SN2?
Yeah.
So I just wanted to point out these variations. In the first reaction, we just did a plain SN2 in one step. In the second reaction, first we did the SN2, and then we did an acid-base reaction. And in the third set of reactions, first we did an acid-base reaction, and then we did the SN2. This is one thing that frustrates students, so there's so many different variations on when you do the acid-base reactions. But notice, even though I don't think you really remember SN2 reactions too clearly, you were able to, figure out all of these just using the basic rules that we've been talking about. You didn't even have to know the term SN2 to pretty much see what was going on here. So we can use the rules we've been talking about to see when we need to do the acid-base reactions and when we do the nucleophile-electrophile reactions. Okay. So let me go back to my screen. Okay, try drawing the reaction arrows here. Let me give you something else. Sorry.
That's okay.
All right, let's try this way instead. Great. I'll go back to my screen for a second. Because H2SO4 is so important, we should memorize its Lewis structure. So here I am on my screen. You can see here's the Lewis structure for H2SO4. You should just memorize that, and that will help you to draw the electron pushing arrows more exactly.
Okay.
So go ahead and redraw the whole molecule so it looks like what we had there. Okay, great.
So the question I have here is, while this water molecule could play the role of a nucleophile, this oxygen on the sulfuric conjugate base could also play it, but it seems like that negative charge is pretty well spread out in that molecule, so I'm not sure which would play the role of nucleophile in this step.
In what way is the negative charge spread out? What's spreading it out?
Resonance?
Excellent. Outstanding. Very good. Well, you and I haven't really talked about resonance very much. That's really good that you were applying that idea in this case. I was just thinking that I hadn't talked about that. So that's an outstanding point. That's good that you saw that. The negative charge there is very stabilized by resonance. That's right. Would that make that negative charge more or less reactive?
Less reactive.
All right, so, so that was an excellent analysis. So it actually does turn out that the negative charge on that oxygen is almost completely unreactive. That's right.
Okay.
It's almost completely unreactive because it's so stabilized by resonance. That's really good that you thought about that. That's something you and I haven't really talked about, so it's good that you applied resonance here. Actually, that's kind of what I'm planning to go over next. After we finish acids, bases, I was wanting to start talking about how resonance can change things. But it looks like you're already applying that to some extent. So that's excellent. The resonance makes a big difference here. So that would alter a lot of things we've said before. When things have negative charges, what role do they usually play?
They usually play the role of either a base or a nucleophile.
But what you just figured out is that if the negative charge is resonance stabilized, it's much less likely to play the role of nucleophile or base, or at least it's less reactive. So that would be another topic for us to talk about, but that was a very good analysis there. In fact, that's so important, I think I'm going to go back to my screen.
Okay.
Just to summarize, this is actually very unreactive because of resonance stabilization, as you just figured out. Or actually, I should say, you figured out it would be less reactive because of resonance stabilization. I had to tell you it would be very, very unreactive. That's not something you can kind of figure out just by staring at it. Very unreactive because of... Now, that's not true for all resonance. I'm not saying that resonance always completely eliminates the reactivity. We should just memorize this reagent in particular.
Okay.
there are resonance stabilized negative charges that can still be reactive. But this one in particular is almost completely unreactive, as you were starting to guess. That was a very good analysis. Okay, so who should be the nucleophile?
Well, this water molecule, the oxygen, could be a nucleophile.
Yeah, that's what I was going for. Yeah. So we're basically never going to use that. What you have there is what's called hydrogen sulfate. Hydrogen sulfate, it basically is not going to participate in the rest of the reaction.
Okay. I do think, though, that if you were to do that, it would give you a product that's exactly the same as this reactant. You would basically be bumping off a water molecule while adding a new water molecule to carbon 2.
Oh, rats. All right. You are absolutely right. You're absolutely right. I didn't mean to write it that way. Thank you. I screwed up. I meant, all right, I'll go back to my screen. So you're right. That reaction didn't make much sense. So basically nothing interesting is going to happen in this reaction. Or actually, you know, what's going to happen in the reaction is something I don't want to... Actually, something does happen here, but I don't want to talk about it. What's going to happen here is something... maybe we'll briefly talk about it. So, let's not even get into it. Okay, I didn't mean to write the reaction this way.
I did have one question, though.
Yeah.
In those starting reagents, I wasn't sure which one should actually be reacting with the sulfuric acid. Did it really matter? They're both alcohol groups.
Yeah, that's a good point, too. Those are a bunch of good points.
Right.
Either of them does seem reasonable here. Do I want to get into this? Let's see. One moment. Let me think about this for a second. What was I trying to do? I thought I had a good example here. Let me think what I was trying to do.
Originally.
Okay, so yeah, let's do it with the two alcohols. Let's assume the alcohol on the left got protonated. Okay. And now let's just try to continue. Good, that's very reasonable. It turns out it doesn't happen quite like this. Okay. Do you remember when we talked about, so what role is the oxygen with the positive charge going to play?
Leaving group.
What makes that reasonable?
Positive charge.
That's right. Do you remember when we talked about that pattern, we said there was actually two patterns. Sometimes the nucleophile will kick off the leaving group, and sometimes the leaving group just falls off on its own. We haven't talked about that too much. But in this case, it turns out that the leaving group is just going to fall off on its own. Okay. Now, I wouldn't expect you to know that. Of course, that's something you'd have to learn by studying the details of the reaction. So I'll just give you that hint. What's going to happen here is that the leaving group will just fall off on its own. So let's draw the arrow for that. All right, you can erase the other arrowhead and then try drawing the product based on that step.
Okay.
Great. Is that a reasonable carbocation?
Yeah, it's a secondary.
Right. You always have to check that. That's one reason it could fall off, because it gave us a reasonable carbocation. Okay. Does it look like we're done?
No, it doesn't, actually.
So now what?
This right here could be a nucleophile and attack carbon 2 as an electrophile.
Great. Outstanding. Good. Great. Great. So what type of reaction did we just do? Nucleophile, electrophile, or acid-base?
Nucleophile, electrophile.
Okay, good. Does it look like we're done?
No, it doesn't.
So what type of reaction do we probably need next?
Probably need an acid base.
Because we just did nucleophile, electrophile.
Yes. So we could use more of this alcohol, couldn't we?
That's right. Or you could use the water. In this case, either of them is reasonable.
Okay.
Either is reasonable. There's oftentimes more than one reasonable way to write a reaction. So you could use either the water or another alcohol, whichever you feel like. Either is fine here.
Okay. I'll just go ahead and leave this.
Mm-hmm.
So it would leave us with a neutral main molecule, which looks like it would finish things up.
Outstanding. That's good. Okay. So let's... I'm sorry?
I just was doubling up on carbon.
Oh, okay. Yeah, it's a little bit better not to double those up. That's good that you were thinking about that. Good. All right, so let's try to zoom out so we can look at this whole thing at one time, if possible. It turned out to be kind of long. How many... Oh, it's a little bit hard. How many steps were there total here?
4.
Okay. Now, one thing I wanted to point out here is, again, there are some exceptions to the rules that we've been talking about. So what did we start with here? Acid base or nucleophile electrophile?
We started with an acid base.
Good. And then notice the next step was a little bit different. Instead of doing a nucleophile electrophile, we just had the leaving group fall off.
Yeah.
That just sometimes happens. That sometimes happens. How do you know when that's going to happen? Well, I can't give you any general rules for that. You just kind of have to learn the specific rules for each reaction. So we're not going to go into that in more detail here. I'm not going to go over any general rules. Sometimes the leaving group just falls off without being pushed. It's a little, there's no general rule for that, although it's only going to happen if it forms a secondary or primary carbocation usually, right?
Yeah.
But it doesn't always happen even when that would form a secondary or tertiary carbocation. It only happens when you can form a secondary or tertiary carbocation, but that doesn't guarantee that it's going to happen. So sometimes you have to study more about the reaction to learn what's going to happen here.
Okay.
So then after the leaving group fell off, then we did a nucleophile electrophile reaction. So one pattern is nucleophile attacks an electrophile and kicks off the leaving group. Another pattern is leaving group falls off first, and then the nucleophile attacks the electrophile.
Okay.
And then we did the acid-base reaction.
Yeah.
You were wondering, in this case, how do we know which alcohol to protonate first? Well, it's a little bit tricky. You might have to learn more about the reaction, but notice if we had protonated the alcohol with carbons 4 and 5, we couldn't form the carbocation then, because it would be a primary carbocation, if you see what I'm saying.
Yeah.
So that's one reason why this way is better. This way is the better thing to protonate, because it gives us, basically, if you don't know who to protonate, you want to protonate the thing that will give you the more interesting reaction. If you don't know who to protonate, you want to protonate the thing that will give us the more interesting reaction. In reality, both of these would get protonated in the beaker. In reality, both of them get protonated in the beaker, but only when we protonate the left-hand molecule are we likely to get this more interesting reaction. So that's the one that's better to protonate. Okay, so I guess I'm trying to give you 2 lessons. One lesson is that the rules that we've learned are very helpful for guessing what will happen in reactions. But the other lesson is you still have to study the reactions. There's still details that you couldn't have predicted. So my point is there's lots of things that we can predict ahead of time about the reaction, but there's also things that you have to learn just by studying the reaction. So you can't, these are helpful rules that we've learned about, but you can't rely on them too much. Okay, so I'll go back to my screen. We also saw that this species is very unreactive despite the negative charge.
Okay.
Try drawing some reasonable arrows here. Okay, that's excellent. That's very good. It turns out this is another case where the leaving group falls off first. But that's not a criticism. There's no way you could have known that. There's no way you could have known that. It turns out that you will learn in OChem that this is a case where the leaving group falls off first. So let's draw it that way instead.
Okay.
So some of these things you can predict, and some things you'd have to learn by studying more OChem. That's fine. Great. Now what? If the leaving group falls off first, then what happens next? Then you do the nucleophile electrophile reaction. Okay, good.
Okay. Yeah.
So the first step you really couldn't have predicted, but the second step now is very predictable.
Yeah.
So let's continue.
Okay.
Okay, so are we done?
I don't think so. No.
So let's try to continue. You just did a nucleophile electrophile reaction, so now you're doing acid-base. That's good. And I noticed you didn't use the chloride. I don't know if you thought about that, but we know that chloride is actually not a very good base. We talked about that. So it's good that you're using the water instead of the chloride. Good?
Okay. Yeah.
Okay, so now, great. Does it look like we're done?
Yeah.
So let's scroll out. I mean, zoom out so we can see the whole reaction at one time. How many steps were there in that reaction?
Looks like 3 steps.
Good. Now, the first step would have been hard to predict without studying more OChem. I had to kind of tell you the first step. But notice, after I gave you the first step, you figured out the last 3 all on your own. All right, so we can't expect perfection here. We still have to study more OChem, but we certainly started making lots of progress. There was actually only one step here that you couldn't have predicted on your own. The rest were all, you could all figure out even if you'd never studied that reaction before. So good, that was a good application. All right, I'll go back to my screen.
All right.
Okay, let's try predicting what will happen here.
Okay.
So you started with an acid-base reaction. That's guaranteed because we had a strong acid. Whenever there's a strong acid, the first step is a piece of cake. Whenever there's a strong acid, the first step is always an acid-base reaction. Good? Okay, so are we done?
No.
Okay, so let's try to come up with another step.
Okay.
Great. Does it look like we're done?
Yeah.
Excellent. Very good. Well, notice this is a reaction, we haven't talked about. You might not have seen this before, but you basically figured out everything that would happen in this reaction. Let's zoom out a bit. Do you see this is actually not the same as what we did before? All the previous examples were alkyl halides and alcohols. This is the first example I've given you with an ether. Here we have an ether, but you figured out what was going to happen using these rules. That's great. Okay, very good. All right, I'll go back to my screen. Okay, try this problem. Let's try to come up with some reasonable arrows.
Okay. Okay. I'm not quite remembering if that were to happen. I know that there's a strong base being one of the Grignards or the...
Okay, so what's the one atom that we can be pretty confident is going to participate in the first step?
Something with a negative charge?
Yeah, well, in this case, the H minus because it has the negative charge. I'll go back to my screen. So this is, I told you I didn't expect to have this memorized yet, so this was a little bit of an unfair question. But going back to our table, what does this table tell us? NaH, what are we going to start with when there's NaH?
With acid base.
Yeah, I shouldn't really expect you to have that memorized yet. I said that was a little bit tricky. But anyway, this is something that NaH pretty much always acts like a base, not as a nucleophile. NaH almost always acts like a base, not like a nucleophile. That's really not obvious. We know that bases are trickier than acids. But NaH almost always acts like a base. I think that's what you were starting to figure out anyway. So it looks like you were on the right track there. So that's good. So let's continue with that.
Okay. Okay.
So are we done or should we continue?
I think we're done.
Excellent. Good. So let's zoom out so we can look at this whole thing. Okay. Yes. So H minus is H minus is pretty much always a base, never a nucleophile. H minus is always a base. NaH is always a base, never a nucleophile. That's in the table, that we haven't worked too hard on memorizing that yet. So first you did an acid-base reaction, and then what type of reaction did you do second?
Nucleophile, electrophile
That's
reaction.
our general pattern. Good. Okay,
Yeah.
so again, we're not promising that, obviously we can't just stop here and not study any more OChem. We are going to have to learn more OChem, but we can see in many cases we can predict ahead of time what's going to happen. And even if we can't predict ahead of time, this is going to help us to see the patterns in OChem and make everything so much easier to remember. The reason why people have such a hard time remembering all the reactions is because they don't see the patterns and they're trying to memorize every single detail. For example, most students don't realize that you're supposed to alternate nucleophile, electrophile, and acid-base. That in itself should make it so much easier just to remember all the reactions. You can see, if you didn't know that you usually have to alternate nucleophile, electrophile, and acid-base, you see kind of how much more memorization there is in the course. All right, so this should all make it much easier to memorize the reactions as you're going through the rest of OChem. And in many cases, you can predict what will happen even before you've studied the reaction. Now, what role did the main molecule play in the first step here? Or what happened to the main molecule here first? Was the main molecule reacting with an acid or a base?
Base.
What did the base do to the main molecule? What charge did it give it?
Negative.
And then that made the main molecule play what role in the next step?
Nucleophile.
This is a really crucial idea then in OChem. Bases make the main molecule into a better what?
Nucleophile.
That is a really crucial idea to write down for organic chemistry. Bases make the main molecule into a better nucleophile by giving them negative charges. Bases make the main molecule into a better nucleophile by giving them a negative charge. That comes up all the time in OChem. So if you don't have a good enough nucleophile, how can you make your main molecule into a better nucleophile?
You could deprotonate it.
Right. Or to be specific, add a base is what I was going for.
Okay.
How can you make your main molecule into a better nucleophile? You would add a
base.
Look at the previous example that's also on your screen. In that case, what did the main molecule react with?
Strong acid.
Good. And then what role did it play in the next step?
Electrophile.
So acids make things into better whats?
Electrophiles.
And leaving groups, as you can see.
Yeah.
So if you don't have a good enough electrophile, how can you get a better electrophile?
Add an acid.
And if you don't have a good enough leaving group, how can you get a better leaving group?
Add a base. Or leaving group, sorry. Also add an acid.
Notice that the acid kind of kills two birds with one stone, if you see what I'm saying. The acid made carbon-3 into a better electrophile and made the oxygen into a better leaving group. So acids kind of kill two birds with one stone. They give you usually both a better leaving group and a better electrophile. So how can we get a better, if we don't have a good enough electrophile, how can we get a better one?
If you don't have a good enough electrophile, you can add an acid.
And how about if you don't have a good enough leaving group, how can you get a better one?
Also add an acid.
And how about if you don't have a good enough nucleophile, how can you get a better one?
Add a base.
So that's one of the most important principles in organic chemistry. Remember that actually in organic chemistry, many problems are synthesis problems, where you have to come up with even the reagents on your own. So it's important to know when you need to add an acid or a base to help your reaction work. So these two examples here summarize, you can write down what we just talked about. Acids make things into better electrophiles and leaving groups. Bases make things into better nucleophiles. We'll talk about that more as we go on, but that's a very important principle. I'll go back to my screen. Okay, try to predict what's going to happen here.
Right.
Nope.
So the first step is an acid-base reaction. That's a no-brainer because we have a strong acid here. Strong acids always start with an acid-base reaction. Good. All right, are we done?
Not yet.
Okay, so let's continue. Great, are we done?
Yeah.
Okay, this is actually quite different from the earlier reactions. We hadn't done any reactions with alkenes before, but you figured out the whole reaction here, what was going to happen, just using the principles we talked about. So that's very good. I'll go back to my screen. All right, let's try this one example. How many charges do we change on every step of every mechanism?
Yeah, just getting to that.
Okay. Oh, sorry.
That's okay.
Although it is always good to first finish drawing the products from the previous step before you start drawing the new arrows.
Oh, okay.
Because otherwise, how do you know what the arrows are going to be? Okay.
True. Thanks. So I guess at this point, that sulfur-based molecule would be just a spectator.
For that step anyway. Good.
Sure.
Okay, are we done?
I don't think so. Looks like if this pattern holds true like we did before, that could fall off, although we did just do a electrophile nucleophile reaction. If that's the case, we would do an acid base, use another Okay.
Are we done?
Yeah.
Okay, so let's look at this whole thing. How many steps were there?
3.
Good. All right, and you got all of those steps correct. So that's excellent. You figured out this whole reaction. I don't think I gave you any hints. Just using the rules that we've talked about, you figured this out. That's good. So you started with an acid-base reaction. That was a no-brainer because we had a strong acid. Then you did nucleophile, electrophile. Now, your analysis for the third step was really, really outstanding. So let's we're so good at it. The key thing is at first you weren't sure what was going to happen in the third step. At first you were thinking, well, maybe the leaving group should just fall off. But then what you did was very good is you applied what we've been talking about. You asked for the pattern. You said, what did I just finish doing? You said to yourself, I just finished doing a nucleophile electrophile reaction. So what should come next? Acid-base. So that might not seem like a big deal, but it's very good that you're actually using the techniques that we've been talking about. It's easy to forget those. So that's very good that you actually used what we talked about. You asked, what did I just do? Nucleophile electrophile. So probably now I need an acid-base reaction.
Okay.
So that was a very good analysis of that. Also, by the way, maybe you noticed this. If the leaving group had fallen off, it would just have taken you back to the previous picture.
True.
So what's the point of doing that? That's another principle. There's no point reversing the step you just did. Okay. Also, something else you did, you remembered that we don't use the hydrogen sulfate. You remember that, as we talked about earlier, the hydrogen sulfate is resonance stabilized and is extremely unreactive. So you used another water molecule in the acid-base reaction instead of the hydrogen sulfate. So that was very good. It's good. There was a step that gave you trouble, but you just took your time and you thought about it rather than just taking a guess. It's good that you didn't take a guess, but you thought about it. All right, I'll go back to my screen. Actually, there's something else I wanted to mention on the previous problem.
Sure.
What role did the alkene play in the first... Actually, let's go back to your screen. First of all, yeah. So what did we react the alkene with in the first step?
The alkene reacted with the sulfuric acid.
And that made the alkene into a better what?
Electrophile.
So that's just an illustration of what we were talking about a few minutes ago, right?
True, yeah.
By reacting with an acid, we got a better electrophile. Was that important? Well, yes. Could the water have attacked the alkene in the first step?
No.
No. So you see how crucial the acid was. If you were trying to set this up on your own as a synthesis, you wouldn't get anywhere if you only put in the alkene and the water, because the alkene is not an electrophile. But how can we make things into better electrophiles?
By adding an acid?
And that's what happened here. Okay, good.
Yeah.
Now, by the way, then, what role did the alkene play in the first step?
It was a base.
That's right. But maybe now I'll go back to my screen. Is there anybody else who could have been a base in that first step besides the alkene?
Water.
The water. Did you think about that? So that's something we should have considered. Should we protonate the water instead? So why would you reject that? I'm not sure what your thinking was, but there's two reasons not to do that. First of all, you don't usually do steps that ignore the main molecule. If we just protonated the water, the main molecule would just be sitting here like a spectator. That doesn't usually happen. Usually the main molecule is involved in every step of the reaction. That's just a problem-solving technique. So it would be weird to just have these two guys reacting with each other while the main molecule sits on the side twiddling its thumbs. So that's one reason not to do that. But the other reason is, if you had protonated the water, there's nothing you can do in the next step. Remember, this is an acid-base reaction. What do you usually do after an acid-base reaction?
Nucleophile, electrophile reaction.
But there isn't really any way here to do a nucleophile electrophile reaction between these molecules. Actually, the only thing that this could possibly do now is this, if you see what I'm saying. But then you would just end up protonating, then you would just end up doing another acid-base reaction, really.
True, yeah.
Okay, so sometimes, what do you do if you're not sure who to protonate in the first step? Well, protonate the thing that will give you an interesting reaction for the second step. That's another rule. If you're not sure who to protonate in the first step, you should protonate the molecule that will give you an interesting reaction in the second step.
Yeah, it seems like it would be a little odd also to, in the presence of a strong acid, create a new strong acid. Is that...
Well, I don't want to emphasize that too much, because remember, technically, this is a strong acid too.
True, because it has a positive charge. Okay.
That's right. So that's maybe not the best way to think about it.
Okay.
Okay, let's try predicting what will happen here.
Oh, sorry, I didn't quite get that.
Oh, yeah, sorry.
That's okay.
Go ahead, take your time.
Thanks. Okay. Got it.
try to come up with some reasonable arrows.
Okay. Electron.
So what role did the oxygen in the alcohol play in the first step?
Base.
Good. Is there anybody else who might have been a base in the first step?
Well, we talked about the oxygen and the carbonyl not really playing the role of base or nucleophile. Typically, it would be. Well, wait a second.
So what we said is that it doesn't play the role of nucleophile. It actually often is a weak base. I know that's confusing.
Okay,
but yeah. We said it's never a nucleophile. It's often a weak base. So here we have a problem. It's not really obvious who should be protonated.
True.
So
yeah.
what you need to do is you need to protonate the thing that will give you an interesting reaction for the next step. You need to we have two oxygens that both seem like good candidates for being protonated. We have two oxygens that both seem like good candidates for being protonated. So you need to protonate the oxygen that would give us an interesting nucleophile electrophile reaction in the second step. Now, it might not be obvious to you which one that is, so you might just have to try them both by trial and error.
Yeah.
So let's stick with the way you have it so far. What would happen if you protonate the alcohol oxygen? Will that give us an interesting reaction now for the second step? Go ahead and draw the products from that.
Okay.
How many hydrogens are on that oxygen?
Sorry. Thanks for catching that.
Okay. So now what role would you expect carbon 1 to play? What role would we expect carbon 1 to play in the next step?
Electrophile.
Good. But are there any reasonable nucleophiles around?
Actually, no.
Because we've said that carbonyl oxygens are usually not nucleophilic, right?
Okay,
We've said that carbonyl oxygens are usually not nucleophilic. You may as well also draw the hydrogen sulfate since that was produced. But we know hydrogen sulfate is highly unreactive.
Okay.
Okay. So, did this seem like the right oxygen to protonate?
No, it didn't.
So let's try the other way and see if that gives us a more interesting reaction.
Okay.
Okay, that does seem totally reasonable. That's a totally reasonable step that you now drew here for your acid-base reaction. That's not conventionally what's drawn here, although that is totally reasonable. Conventionally, we just draw the alcohol again to deprotonate. But either of those could happen. Both of those are reasonable. What you drew, actually, I don't think you would lose any credit for that, but that's not usually what you would see in the answer key. So remember, oftentimes there's more than one thing that can do that last deprotonation step. So what you drew actually made good sense, but to make it look more like what you would see in the textbook, we'll draw it this way.
Okay. Okay, looks like the main molecule no longer has a charge. So that looks like it's done.
Okay, excellent. How many steps were there?
3 steps.
Okay, good. Now, this is a reaction I know you've never seen before. This is a second semester reaction, so we should take some satisfaction that we were able to guess or figure out what would happen here. So that's very good. Now, on the other hand, of course, it took some work. So maybe you might want to label up above. Remember that at first it wasn't clear who we should protonate. You might want to label that your first try turned out to be a dead end. That wasn't the real reaction. We rejected that first one up above because it turned out to be a dead end. There wasn't anything interesting we could do after the first protonation. Okay, so if you're not clear who to protonate first, try to protonate the molecule that will give you an interesting nucleophile-electrophile reaction in the second step. And if it's not obvious which one to use, you might have to do some trial and error. Of course, once you start, you'll have a big head start again in OChem because once you start studying this reaction, you can also kind of memorize what to do. But the point is, this reaction will be way, way easier to memorize if you're understanding how it falls into the general patterns that we've seen. So you're not going to be relying purely on these rules in OChem. You're also going to be learning what happens in the reactions, but it will be so much easier to remember if we see how it falls into just generally what we would expect. Now, what did we learn here about carbonyl? Well, what role did the carbonyl play in the first step?
Base.
And then that made it into a better what for the second step?
Electrophile.
That's right. That's the general pattern we've seen before. Carbonyls are actually already electrophilic. But how can you make a carbonyl into an even better electrophile?
Adding an acid.
Exactly. That turns out to be, I think I mentioned to you that carbonyls are kind of the most important functional group in the second semester. So a huge percentage of the reactions in the second semester start by protonating carbonyls. So that'll be something you'll get much more comfortable with as you go through the second semester reactions. So to summarize this, carbonyl oxygens. Do carbonyl oxygens often play the role of a weak base?
Yes, actually, they do.
Do they often play the role of a nucleophile?
No.
In fact, I'm going to go ahead and say, in an introductory course, almost never. In your introductory course, I think you might never see an example where a carbonyl oxygen is a nucleophile. Now, that's not, you wouldn't have predicted that based on our rules. Based on our rules, you would expect this to be a pretty good a decent nucleophile because of the lone pair. So we'll just have to memorize that as an additional rule. It turns out that carbonyl oxygens almost never play the role of a nucleophile in your introductory course, but very often they're a weak base. So that's a new idea we hadn't talked about before. Okay, well that's our time for today, but I think now we've made some really good progress here. We're starting to integrate. You see, we're basically now, in these last hour or so, we've been integrating everything we've talked about so far, the nucleophile, electrophile, and acid-base material. And we're getting to the point where we can oftentimes take really good guesses as to what's going to happen in a reaction, even if you've never studied it before. So obviously, once you actually start studying the reactions, then this will be even easier, but it'll be much easier to understand the reactions and to remember the reactions, so that we're not relying purely on memory. Also, you might not even have thought about it, but something you were doing on all these problems that most students can't do is you were drawing the products based on the arrows, right? After you drew the arrows, you were drawing the product. Most students can't do that. Most students can't actually draw the product based on the arrows if they haven't seen the reaction before. But that's what we went over in our first couple of tutoring sessions, and it looks like you still have a really good recollection of that. In fact, I don't think you made any mistakes, or very few mistakes on that. So we integrated all the different ideas we've been talking about. We've been using the rules we talked about to predict the arrows, and then we've been drawing the product based on the arrows. Notice that oftentimes I kind of had to give you some help on the first step, but then the other steps you were usually able to figure out. So oftentimes, to figure out the first step, you need some extra help, or you need to learn more about the reactions that you'll study in OChem. But the rules that we've talked about here can be especially helpful in figuring out what happens after the first step. And they can also help you to remember or guess what might happen in the first step as well. Okay, so obviously you want to review this material, so we don't have to keep going over it too much more together. Let's see, so we talked about, what did we talk about? Talked about how a weak acid doesn't react with a weak base, but these reactions do happen. You have to memorize this table. You have to know what the strong acids and strong bases are. Remember, not everything with a negative charge is a strong base, so this table has to be memorized after today's session. What else did we talk about? We talked about this very important pattern. Very often in OChem, you do a nucleophile-electrophile reaction, then an acid-base, then a nucleophile-electrophile, then an acid-base, then a nucleophile-electrophile. There's exceptions to this, but this is a very useful pattern that came in really, we were really getting a lot of mileage out of that. You usually stop when the main molecule has no formal charge. You were doing a good job of applying that rule. Now this table here is kind of complicated, but you might want to kind of sit and meditate on this a little bit. This idea is very simple. When there's a strong acid, you always start with the acid-base reaction. Then if you have a strong base, it's a little bit more complicated, but you might want to kind of stare at this a little bit and try to memorize this a little bit more. That unfortunately it gets a little bit complicated for strong bases, but you can take your time and think about that a bit. And then we did a bunch of examples, and we were seeing that in many cases I had to give you a hint or a clue, but in many cases you were able to take some good guesses as to what was going to happen. And also we saw a few more rules. Halogens, negative halogens are very poor bases, but they're excellent nucleophiles. You wouldn't really predict that based on the other rules we talked about. That's just an additional rule. We talked about how this is very unreactive because of resonance stabilization, either as a nucleophile or a base. We talked about, I can't find it now, but we talked about how carbonyl oxygens are weak bases but not great nucleophiles. So we talked, there's plenty of stuff for you to review after today's session that'll come in handy for you.
I was wondering, I noticed like when you would have an acid-base reaction to begin with, you could have a lithium aluminum hydride, but would an alkyl lithium cause the start to be a acid base?
If you have an alkyl lithium?
Yeah.
Sure. Well,
and I can ask it next session too. That I just had that.
So here's the rule.
There it is. Okay.
An alkyl lithium will be a base if there's an acid around.
Of a weak acid. Okay.
But that's not usually what you want as a chemist. Alkyl lithiums were invented to be nucleophiles. So what you will usually do is you'll use an alkyl lithium and you'll be very careful not to include any acid.
Okay.
So that you'll get the nucleophile-electrophile reaction. So the only reason we need to know that this can happen is so that we can avoid it, kind of, so to speak. You have to keep alkyl lithiums away from acids so you can get the reaction you want, which is the nucleophile-electrophile. I think we'll go into this in more detail next time. So maybe we'll talk about that in more detail next time, but that was a good question.